Our next presentation is on virtual reality for baseball pitching biomechanics, and I don't know about you, but I've been kind of looking forward to this one. We're welcoming Eric Bubar from Marymount University, who is the founding professor of the engineering area at Marymount University. And I love this phrase, dedicated to democratizing engineering education by making it accessible to all through open source hardware and software. Eric, welcome. Join me in welcoming Eric.
Can't claim all the credit for that biography. I used ChatGPT for some of it. So I'm going to talk to you about virtual reality for baseball pitching biomechanics. This is a project that we started basically in August of this past year, and it's a collaboration with Marymount baseball team. Our team right now is myself, Anthony Bartuch. He is helping to develop a instrumented baseball that we can put into VR. And then the brains behind all of this is Shane Halley. If Shane, can you raise your hand? Look at the back of the room. He's our baseball coach or assistant coach, but amazing. So let's hear about Shane. University Athletics pitching coach. 2 ACC championships, 2 appearances in College World Series, the Royals and the Rockies. And I think I found a picture of you pitching. That's it. Yeah. Google's got some amazing tools. I think Shane heard that there was a new engineering program. So I came into my lab one day and I was getting ready to teach a class, and he was there waiting for me. I'm like, oh, hey, how you doing? Nice to meet you. And he had this idea. He was like, so I heard you're an engineer and you can do lots of cool things. What I want to do, I want to measure ground reaction forces. Now, we just started an engineering program. So prior to that, I was teaching only biologists. So nobody liked forces. Nobody liked ground reaction forces. Everybody hates physics there until 2 years ago. So along comes this guy and he's like, I want to measure these forces. I'm super excited. So I'm like, yeah, I think we can figure out a way to do this. And then we started talking more. I started telling him the kinds of projects that we work on. And I'm like, well, maybe we can do more than that. Maybe we can get biomechanics. Maybe we can do some ball physics and track like balls rotating around and how all that works. Here's an idea. Maybe we could do a VR pitching simulator because I wanted to play in VR. And he got very excited because there's this VR tool that already exists, and we'll tell you a little bit more about that. So here's what we've got. We've got gold standards versus accessibility for doing biomechanical analysis. Right? So ground reaction forces, if you want to measure those, standard is to use something called force plates. These are about $100,000 a pop, and you need a few of them. So that's quite expensive. To do biomechanics, you need high-speed motion capture facilities with marker-based tracking. So if you watch TV, watch like The Mandalorian and stuff like that, they put these dots on you and track your movement. That's the kind of technology we're talking about. That's $1 million plus. Ball physics, you need high-speed motion capture tracking, radar tracking, or IMUs. There's actually a baseball that we have now on campus. It's about $500. You can buy it, and it will do all sorts of rotational analysis for you. And then a VR pitching simulator, that doesn't exist. There is a tool called WinReality. Anybody ever used WinReality? It's available on Quest. You can buy it. You attach the controllers to a bat, and then you can get really pretty accurate batting simulators for doing batting training. But VR pitching doesn't exist. So gold standard kind of stuff, that's going to be about $1 million. Marymount is not going to spend $1 million on this. So how do we do it for low cost? So ground reaction forces, I was a physics teacher, so we had teaching grade force platforms from Pasco Scientific. So those run about $1,000. So it's a force platform, not a force plate, a little different, but we can get ground reaction forces both perpendicular and parallel to the motion that you're doing. So we can get ground reaction forces, great. Biomechanics, there's a tool called OpenCap out of Stanford, so we can use that and a couple of iPads to do motion tracking. But what if we could use just a VR headset? So let's see if we can do that. I had a Quest Pro and a Quest 2 at the time. So we did some experiments with that. I'll talk about that in a moment. But it turns out Quest 3, maybe we can do some more with that. For ball physics, we need IMU tracking and virtual reality ball physics. So about $30 for an Arduino. and a 3D printer and somebody that can do some CAD, go to your kitchen, 3D print your baseball, and maybe you have a instrumented baseball. And then the VR pitching simulator, that is the Unity software development. The latest Meta SDK, and when I say latest, I mean June, so a month ago. And then my time. So how much does that cost? That's about $1,500 plus, I'm priceless. Right? So what did we do? So turns out Shane's, I think your father-in-law, is an engineer. So I got the force plates, and then they got out the pitching mound, started chopping it up, and installed the force plates. So we can get ground reaction forces for pitchers now for about $1,000 bucks. Super great, nice. We need to, if anybody knows anybody at Pasco, tell them we're doing this so that they send us more stuff for free. Okay, so ground reaction forces, done. Easy peasy. Biomechanics, I call it maximum biomechanics with minimal VR. So we have the minimal amount of tools we can use. So pitching, very complicated movement, very tough to analyze, very fast, very high-paced. Turns out if you read some papers, professional pitchers and some of the college players that we're working with, they will have those kinds of qualities of professional pitchers. They are rotating their arms with the fastest, the shoulders, fastest human motion that's been recorded. It's about 8,000 degrees per second. They've done studies of cadavers and found that a professional baseball pitcher is actually flinging their arm faster than the bones and ligaments should be able to hold it. They move these cadavers at the same speeds as pitchers, and they break their arms. So we got to try to measure that. Okay. The baseball pitching biomechanics, very complicated. It's actually energy transfer that's moving from the ground, through your legs, through your hips, through your torso, through your arm, through your wrist, and you're transferring that energy the whole time. So energy is building up, right? A pitcher doesn't get out there and just go, they're not going to throw at 100 miles per hour if they do that, unless they pay my pitching game and I tweak the numbers, okay? So we have to kind of measure all those energies and transfer all those energies and see if we can do that. For the lower body, can we do that with Quest? We cannot. So Quest does have inside-out body tracking, but it's feet algorithms, and they will tell you this in the documentation. It's basically guesswork. We can't use that. It's not accurate enough. We'd require some additional trackers, something like Sony MocoPi, so you can get additional IMUs, basically, that you attach to your lower body. And we can maybe get the data that way. Or if we want to go open source, we can use Slime VR trackers potentially, or external cameras, something like a Vive that has base stations. Maybe we can do better full body tracking, but again, I don't have the budget for that. So maybe we'll explore that later on. So what we took off with is what can we do with the upper body? So with the upper body, with Quest inside-out body tracking, so this is only Quest 3. It does not work on Quest 2. It does not work on Quest Pro. We can get positions, rotations, and velocities for the hips, the shoulders, the arm, and the wrist. Okay, we can do all of that, and we can start to try to measure some biomechanics. So what did we do with this upper body stuff? Here's our first trial. This got Shane really excited in fall 2023 when I showed it to him. He thought this was cool, and this made him think of lots more ideas to keep me busy for several more months. Theme music.
So there's a proof of concept for the VR pitching simulator. We've got hands, we've got mood music, and we've got data that we can track. So I can pick up a baseball, I can pitch it, and it'll tell me what the maximum velocity and acceleration are that I get. And then the ball, as I throw it, once it hits the back plate, will kind of respawn. So I can do this an unlimited amount of times. And what we got to work on now is lots of physics to accurately track these balls, get the physics actually working right, and get the actual velocities and kind of data that we're aiming for. There's a proof of concept for you.
So proof of concept, built it in a weekend. Great. So let's see what Shane thinks. Shane gives me lots of ideas. I'm like, okay, I built this in a weekend, so this should take me a couple more days to get exactly what he wants. Yeah, no. Okay, so this is kind of what we started thinking about. Can we get biomechanics data out of this? Can we do this without controllers? Can we make you see the real world? Can you use pass-through for this? Right, so we can take it to an actual stadium. And can we get the ball to rotate and get all of that data too? We want all the possible data that we can get. Right, more data, always good. So this is the data that we're trying to get. This is something called the kinetic chain or kinematic sequence. It's the sequence of movements that you have for baseball pitching. There are different distinct phases, and they've broken this up, and this is very, very well studied. Major League Baseball, again, they use $1 million facilities to do this. Let's see if we can do it with the $500 headset. So basically the first half, we can't do anything with that, right? Because that's all based on the lower body. Second half, we can start to do things with. Okay? We want to optimize, use this to kind of measure this kinematic chain so we can optimize it for all the players, make sure that they're not injuring themselves, and give them a chance to kind of practice pitching in a small place, right? They don't always have access to a big, gigantic field to start flinging balls at 100 miles per hour. They can't sit in their dorm rooms and do that. What happens if they stand in their dorm rooms and start flinging baseballs at 100 miles per hour? They start damaging stuff. We don't want that. But what if they can do that in VR? They can do that in their tiny little dorm rooms safely. Okay? So how do we do this? How do we track this with the kinetic chain with the VR headset? So we're basically going to start at the point of foot contact, where your arm's back. We're going to measure maximum arm cocking phase, so that it's your arm slingshotting around and your hips rotating and your shoulders rotating, your arm slingshotting, and then flinging your arm forward, releasing it at the right position, at the right time, and measuring the rotational velocities of all of these portions of the body while you're doing this. So can we do it? Actually, I say yes, but you're going to answer this for me. You're going to tell me if we can. The graph on the left is motion capture data. So that's the pelvis, torso, shoulder, and hand being rotating around during a pitching sequence. All those different colors are the different portions of the body. Bubar mocap is on the right-hand side. So that's what I measured out of the Quest. Qualitatively, they look similar to me. They look close enough. $1 million on the left, $500 on the right. And we're getting about the same kinds of information, right? It's not as accurate, but what we care about is it good enough to make a difference and improve outcomes for our players, improve their performance, and decrease their incidence of injury? Is this enough? Is this good enough? Things that we found, we can track the kinematic chain with just the headset and controllers. We do need to use controllers. Hand tracking isn't good enough because you're putting your arms behind your back, so the cameras can't track that. We need the controllers for that fidelity. You have to use Quest 3. Does not work at all on Quest Pro. Does not work on Quest 2 because it just doesn't have the tracking. It's just not good enough. Quest 3 is, as of their June update. It seems pretty good, but it is proprietary, so we need to assess if the angles that I'm even getting out, do these even make sense? Are they accurate? Are they correct? Let's figure that out. How can we figure that out? So I'm going to call it a silver standard. So we can measure range of motion, so we can measure angles of all of our joints, and we can do that with motion capture. That would be maybe a gold standard. Jenna is here. Jenna helps with this research. Jenna, raise your hand. Say hi to Jenna. If you have questions about this, you can ask Jenna later too. I call this a silver standard. I think PTs would probably call it a gold standard as well, but I think it's a little less than mocap because it's not as cool technology. Goniometry, it's a fancy protractor, and they use it to kind of align different parts of your body to measure what angle my shoulder is at. So I can measure ranges of motion. So let's see if we can do that exact same thing using the exact same kinds of information that we're getting for the kinematic chain, and let's see if we can figure out how accurate our angles are. So let me describe our little process here. For measuring angles and finding range of motion in VR. So you got the VR headset, you got the two controllers, and a AI that is fit to do inside-out body tracking, so it's using these cameras to kind of look at my upper body. And I can use this to calculate all of these angles. So on the actual size
on the computer screen, if Jen is pointing at that, you can see right elbow angle, left elbow angle, right shoulder angle, and left shoulder angle. So it's getting all of these angles at my shoulders and at my elbows.
We can get more angles if you want that. But for this proof of concept, that's what we're doing. Okay, so we can measure all of these angles out, right? And we can do it very, very quickly. So we've done that. We've done 3 different trials. Oh, I guess I have another video. When we're using this to actually measure the angles with Jenna, Jenna will have me do a pose. So maybe she'll have me do shoulder flexion. So I get my shoulder up, and I can see that my right elbow angle is about 179-ish. When I'm actually doing this, we're going to repress those angles so that the person doing it doesn't actually see it. And when I want to log an angle, I can just push a button on the controller, and that'll log that value to a file, and I can keep logging a bunch of angles. So I can keep logging those angles so I can get a whole bunch of measurements super, super, super quickly, so that I can get some idea of a standard deviation of the angle measurements that we're getting from the headset. So every little flash that you saw on that screen was me logging the angle again. So I'm just measuring that angle, see how consistent it is, see how stable the measurements are. So we could use this to automatically get a range of motion for anybody that's in VR, and we can do it very quickly. So I can put my right shoulder flexion and log it. I can do left shoulder flexion and log it. I can do right elbow extension and log it. Abduction, log, abduction, log. I can do shoulder flexion and shoulder, or elbow flexion and elbow extension as well. So I can do log it, extension, log it. So I can get data really, really, really quickly. Okay, so I did a full range of motion assessment there in about a span of a minute. And we got a bunch of data for that. And then we can show you some of this. So none of this is published, so don't tell anybody. The go columns, those are measured with the goniometer. So that is Jenna coming into the screen and measuring with the goniometer, my left shoulder flexion, extension, all of those values for left and right shoulders. And then the VR columns are me measuring that with VR. Okay, so we can kind of compare the numbers. There are some strange things happening that we figured out. Occasionally, Jenna would get into the view of the camera, and she'd be measuring the angles, and that would confuse the inside-out body tracking, so that would throw off some of the numbers. So we figured out that little problem. One of the big advantages, I think, is it takes about 10 minutes to do a range of motion assessment for Jenna to make all these measurements. How long does it take me to do it with just the VR? A minute. So I can get 10 different values, 10 different trials in the span that Jenna can get one. Yay, tech. Okay. So what we need to do now is we need to actually maybe do a bigger study and kind of start to quantify some of these angles, see how good they are, see how accurate they are, and then start doing this a little more formally. So current answers to all of our questions that we started with. Can we get biomechanics data? Yes, we can. But what we need to do is, I think, probably get a convenience sampled pilot just so we can get a lot of people in quickly and figure out the accuracy and precision of this data that we're getting, all these joint angles. And then we can do a power analysis to inform a larger blinded study to really form that out. Can we do this without controllers? No, we cannot. We need controllers for that sensor fusion to get that accuracy. Otherwise, this is not going to work. Can we do this with a headset other than Quest 3? Not any that I have access to. Can't do it with the 2, can't do it with the Pro. Can you do this with the real world? No. Why can't we do it with the real world? Why can't we use pass-through? Cameras are busy. What are the cameras busy doing? Tracking my arm. How fast is my arm moving? Do you remember that? 8,000 degrees per second. No, mine probably like 100 degrees per second. But with the professional player, like we have in the back, moving really, really fast. So we need those cameras to measure that. Now, can we get the ball to rotate and measure that data too? This is a firm maybe. So Anthony worked on this. So what we've got now is an Arduino Nano 33 BLE. So that's Bluetooth with this specific IMU. It can track up to 16 Gs. It's pretty good. So what we've written is Python to read the raw accelerations and rotations, Python to process that, filter the data over to Unity through UDP, then displayed that real-time motion in Unity eventually, accurately, and then maybe some Kalman filters, and I think we need some additional sensors for the position tracking. It's just too noisy to integrate the acceleration to get up positions. But there are some options for position. Maybe a camera, we got a little camera up there, or some radar tracking somehow. So we can show you what we've got so far. This was largely Anthony's part of the contribution. I do want to give him credit. He is an IT and cybersecurity major, so I'm confident that our ball cannot be hacked. But it doesn't quite work right. I'm not doing anything on the keyboard. That is responding to the IMU. It's not tracking exactly right, but we are getting some results. Okay. Famous last words, give me another week and I'll have that working. All right, so what I can do now is plug a wonderful demo. This is the first version that we had. I have since, I had a couple days after we got back from our vacation in Scotland earlier this week, and I've upgraded this a bit. So what you can do is you can come over and see our demos. We've got it set up so that we will plot your kinetic chain in real time as you're pitching, so you can see your own kinetic chain. It will analyze and assess that kinetic chain and tell you what you need to change about your pitching biomechanics so that you can improve your pitching speed. It will tell you the velocity that you are pitching at. And if you manage to pitch a strike, you can get a baseball gumball through the magic of Amazon. Happy to take any questions. I think we left enough time for it.
Let me start by saying I don't know exactly what the goal is to measure in those range of motion studies. Is it the actual objective extremes of their motion, or is it where they perceive the maximum to be? Because I imagine that would affect timing in their performance, say when they're releasing the ball. But I was trying to figure out from your video, were you clicking with the opposite hand to tell it when to log, as opposed to having it record the angle at all times, and then you can look at it afterward and extract the maximum or minimum?
Yeah, we could do that as well. We can do either. We are trying to get the maximum that they feel like they are comfortable reaching up to. So that is then their individual ranges of motion.
Okay, so...
What they think they can do, not what they physically can, what they feel comfortable doing.
Okay, so that is the more subjective measure, so then having them control the time when it clicks makes more sense. Okay, thank you.
You're welcome.
Eric, what is the sample rate for the inside-out body tracking, and do you think that that is a limiting factor in your work?
It is a limiting factor. I need to go back into the data and remind myself of what the sampling rate was. I had it, I knew somebody would ask the question, and I forgot to go look, so I got to remind myself. But yeah, that is definitely a limiting factor. So there's a question from the back. What would, actually, anybody can answer this. What do you think the ideal sampling rate would be? Blake.
Twice the maximum speed that you'll need to be able to do, which is the Nyquist rate.
Yeah.
We know, we know from some of our IMU work.
Yeah. So we ideally want twice that, twice what you're trying to sample, and Quest's not going to do that. So filtering data, this is where we're to the point of, right, that's why you pay $1 million to get the accurate, correct data, but is the inaccurate data good enough that you can use it to make good outcomes and make an impact and make a difference? If you make it more accessible, is that more beneficial than having it limited to like 10 facilities in the world? I think so.
So do you actually have student player feedback on this yet at Marymount?
I think a couple of players have gotten in and flung the ball, and I think their feedback has been, this is really cool. So we'll start to get more player feedback. So this started in the fall, and we developed some stuff, and they played that little first demo, and they played with the force plates a little bit. And then spring, I think you were in season, so they were playing, and we couldn't mess with them because they were way too busy. And then now this summer, a lot of them aren't here. So once fall comes around again, we'll start sticking in this, and we'll start getting some data.
I'd love to see data like, hey, a player who could barely get an 85-mile-an-hour pitch is now confidently doing 90-mile-an-hour pitches.
Yeah, and I think that's going to be a longer-term study too, right? Because you don't gain 4 or 5 miles per hour quickly. That's several months. That's a lot of strength conditioning, a lot of additional training from our experts.
Hi, I had a question. You were talking about making a ball that you could also track in VR, but you were also talking about how they can just do it in their dorm. So, like, when you do have that ball, like, what does using the VR look like then?
Yeah. So then, this is Shane's brilliant idea. It's basically, they have tools that people currently use for pitching. You basically, for lack of anything fancier, you stick the baseball in a sock and tie the sock to your arm. So then you fling it, but it just falls. So then you don't break the dorm room, hopefully.
So you said that you have to use the controllers because you can't track the arm without the controllers.
Right.
How do you fling the ball if you're not holding if you have to hold the controller?
So you hold the controller, and you'll see this when you play the game. You spawn the ball by pushing the trigger, and then you release the ball by releasing the trigger.
Okay.
So that's actually a big flaw of the game right now. My wife hates it because she doesn't have the timing quite right. Actually, her timing's probably great. It's the programming is wrong. So the timing is off because of the programmer. So the ball ends up going off to the left because you got to release it a little bit earlier. So that timing's a little bit off. But for the proof of concept, we can get the biomechanics data, and then we get that baseball working.
Sure. I have one more question. Yeah. You said that if you use this demo, it would give you feedback on what you should change to be more efficient at pitching.
Yeah.
What data are you using to determine that? Like, I'm a high school pitcher, and I've had multiple coaches tell me different things. So what data are you saying is the better
So
data?
we are using this kinematic sequence that we're plotting, and the sequence of where the peaks occur, that is the order that you want your body to rotate in. So you want your pelvis to rotate, then your torso, then your shoulders, then your arm, then your wrist. So you want those to rotate in sequence in time. So we can see when things are rotating and when they reach their maximum rotation in the plot. We log that time, and if my shoulder's rotating earlier than my hips, I'm losing energy between those, and the graph can tell us that. So that's pretty easy conditional statements.
Understood. Thank you.
Thank you so much.